Hi everyone, thanks for joining with us today. I'm Prabhat Agarwal, a research scientist at Pinterest, and today we'll be talking about the evolution of web-scale engagement modeling at Pinterest and share some of the most recent work that we have been doing to bring everyone the inspiration to create a life they love. Feel free to ask any questions in the question answer box. We'll be answering them throughout the session and also answer some of them at the end of the presentation. I'd like to start with a shout out and thanks to the amazing team members, both present and former, spanning multiple teams across Pinterest who have contributed to the work I'll be covering in this talk. Today, I'll start by introducing the Pinterest platform and its home feed recommendation system. Then, we'll take a short trip along the history of evolution of this ranking model and our learnings along the way. We'll then deep dive into how we scale this model 4x on CPU, significant engagement improvements, but neutral latency. We'll then share our learnings of how we further scale our model computations with a transformer-based model and enable serving on GPU with minimal latency increase. We'll then end by discussing the new directions we are working on this area to keep making our models better, bringing Pinners new inspiration and ideas. Pinterest is a platform to find inspiration and the tools to realize that in one's life. People come to Pinterest to find inspiration in all forms, from finding what to eat for lunch to planning their wedding. Let's go through an example. This is what a user lands when he opens Pinterest, the home feed. It shows the recommended pins to users based on their interests and past engagements. My home feed here shows the different recipes, dog training ideas for my dog, and since recently I'm redecorating my room, inspiring ideas for the same. Now suppose I want to cook something for dinner. I search for paneer recipes on Pinterest and I'm shown different recipes, different creators, all tuned to my interest. I find one of the suggestions interesting, which is the paneer 65 in this case, and I click on it to learn more. I'm shown the details about the recipe with the step-by-step guide in the amazing idea pin, along with some suggestions for similar recipes that I can explore. I go through this recipe and I like it, and hence I save it to my recipes board. This recipe board is the collection of all recipes that I have found on Pinterest or otherwise, and I like and know it and have saved it for future reference to cook again or to share with other friends. Now with this paneer 65 recipe, I go off to cook my tasty dinner. This is an example of the typical user journey on the platform to find ideas and execute them in real life. More than 400 pinners like me come to Pinterest to find inspiration, to create a life they love, and find the platform to be filled with positivity. Pinners all over the world have saved about 30 billion pins in more than 7 billion boards, encompassing more than 35 languages. And inspiration can take many different forms, and hence is the content on Pinterest. There are native idea pins. There are organic images and videos, often linking to some web pages. There are buyable products. And then there are advertisements. Similar to the variety of content, we have different agents on the platform, each with a different motivation and goal. Creators want to share their ideas and increase their followers and influence. Users want to find and save inspiring content and improve their life. Retailers want to sell a product and increase their gross sales. And advertisers want to increase brand awareness. Hence, the systems that we build need to cater to these different and often competing goals and drive value for all, not just one or the other. Our recommendation systems need to scale to billions of these pins and millions of pinners and find ideas for our pinners fast with around 200 to 300 end-to-end funnel latency. The systems need to embrace multi-objective optimization to cater to the varied goals as outlined earlier. We also want our systems to adapt quickly to the evolving preferences and the needs of our pinners to be relevant and engaging for them. One of the core surfaces on Pinterest is the home feed, which drives the significant fraction of user engagement as well as revenue. It is the first page that a pinner lands onto, and it drives creator content distribution and the user interest discovery through their engagement. The core problem at the heart of Homefeed recommendation system is simple. A user has come to the platform and you need to show different contents. And now to do so, you need to predict for each pin the likelihood that the user will engage with it. So that's basically what the problem is about. This diagram shows a simplified bird's eye view of the system. On the left, there are different candidate generators that shift through these billions of content to find some thousands of pins that might be interesting to the users. Each of these generators focus on different dimensions. For example, some focus on the topics the user is following, some on the creators the user is following, or some on the other users the user is following. And some focus on the user's low dimension representation. These all generators together, focusing on different dimension, allows for a very diverse coverage of the corpus and gives us a set of candidates that can be shown to the user. Then all these candidates are grouped together and fed into the ranking model, which produces a ranking of these candidates based on the predicted engagement probability. This is followed by the policy layer, which enforces different constraints on the ranked pins. For example, we want a certain quantity and quality of the fresh content in the pin, we want some deduplication for the engaged pins, and so on. Together, all this gives you the final home feed where you see the recommended pins based on their engagement probability, as well as the different policy interactions that happen. In this talk, we'll focus on this ranking model, which takes this all candidates generated by the different candidate generators and produces a ranking of these candidates based on the predicted engagement probability. We'll talk about how this model evolved from a simple logistic regression model in 2014 to a complex transformer-based model consuming thousands of raw features to bring the pinners inspiration to dress up their dog in sombrero, to plan their wedding, to decorate their house, and so on. We'll take a brief tour of the major milestones in the evolution of the model and discuss in depth our current work on scaling to thousands of flops at millisecond latency with GPU serving, leading to double-digit improvements in finding the correct inspiration for our pinners. The timeline in the slide shows a summary of these milestones with the corresponding relative increase in engagement to the current then production system as measured through the repin rate on a home feed. We launched our first NN model back in 2014. This model had a small amount of handcrafted features which predicted the probability the user will engage with the pin through any action. It didn't distinguish between the different actions the user can take with the pin. Even though this model was simple, it was a great improvement over the existing GBDT model and helped our pinners find more engaging and inspiring content. This together led to an increase of 7% in the repin rate on home feed. Along with this increase in repin rate, this also opened a new direction for this modeling. And soon we realized that these handcrafted features were not optimal, and we needed a model that can learn these different feature extractors, and hence we started working on a deep network which consumed these raw features and learned interactions between these different features, representing the user's interest as well as the context, in addition to the context in which both the user and the content is. As you can see in the schematic diagram of the architecture, the model automatically learns a summarizing function for the different features for the same type. It then uses these learned representations to cross these features across types. For example, learning the interest between the topics of the content and the topics the user generally engage with. This helps the model correctly learn the user preferences and find the correct content for them. Another milestone for this model was the introduction of the multitask approach. As I mentioned earlier, we were predicting the probability of the user taking any action on the pin, irrespective of whether the user repins it, clicks on it, or goes to a linked web page, or closes up on the pin to see its details. As we can see, each of these different user engagement actions have different properties and different subtle differences between them. Hence, representing them together leads to suboptimal model performance. In this architecture, we separated these different actions and learned an action-specific layer at the end, but with still a shared backbone to promote the sharing between tasks and account for different task imbalance. Together, these improvements led to an impressive 7% increase in ripon rate on Homefeed and improved the pinner's experience on the platform. Another advantage of this model was that it consumed raw signals. This paved the way for us to incorporate many rich features in the model very easily. This led to many improvements along the time, and one of the major ones, which came directly after the model, was the introduction of real-time features over the pin. So earlier, we were not having many real-time features for the pin. In this iteration, we included several performance and engagement features which were calculated real-time for the pin. These features led to a massive 12% increase in the Homefeed retain rate and was one of the most best launches of the year. In the last few years, we started focusing on rich representation of content and users on the platform to power all our models, as it was not feasible to learn meaningful and powerful representations in each model separately. These learned representations can summarize large amounts of information into very low dimensional embeddings. As can be seen, these signals led to massive increase in Homefeed ripon rate, as the rich pin representations provided the model with better content bias, and on the other hand, the user embeddings allowed for better personalization based on the user activity and engaged content. I'll briefly describe how we generate these embeddings for pins and users. More details can be found on our blog and the corresponding publications. We use PinSAGE to combine the content and engagement signals of a pin to produce more comprehensive representations. We utilize the pin board graph and the content features of a pin with a graph convolution network to learn these representations. The main benefit of approach is that by borrowing the information from nearby and related similar pins, the resulting embedding of the pin becomes more accurate and more robust. For example, a bed rail pin might look like a garden fence because they are visually similar, but gates and beds are rarely adjacent in the graph because users save their pins according to some theme and some collection, so they will not say unrelated pins like beds and graphs in the same gates in the same board. Hence, our model is able to exploit this relationship from the pinboard graph to provide the context, allowing it to disambiguate pins that are visually similar but semantically different. Similarly, user behavior tends to be sequential in nature. Actions can be ordered by the time they are taken, which naturally leads to sequentially modeling methods. Hence, to learn a rich user representation, we use a transformer model to encode the user activity and all the engaged content to generate an embedding that can simultaneously predict the user's future, long-term, and short-term engagement. This representation, as said, captures both the short-term and long-term interests and preferences of the user, and hence allows for greater personalization in the ranking model. Adding the PinSAGE embeddings led to an impressive 8% improvement in the Homefeed ripon rate, and on top of it, the PinnerFormer embeddings was one of the biggest launches of the year with 11% boost, demonstrating the effectiveness and power of a rich embedding-based representations. One of the main issues we recognized around this time was that our iteration speed on this model was very slow. The two main reasons contributing to this were complex modeling and serving framework based on TensorFlow 1, and the other one was we had very low correlation between the offline metrics and the online performance of a model. So we invested in resolving these issues, which led to some major improvements in the model, which I will be diving deep in this talk. To enable quicker modeling and make it easy to adopt like different state-of-the-art training and modeling techniques, we migrated to a native PyTorch-based modeling and serving infrastructure. We evaluated several top deep learning frameworks based on different criteria like how easy to learn, what's the performance, and etc., and found that PyTorch was better suited for us in most of these criteria. The performance serving of the native PyTorch, which uses Torch script, meant that developers can now write and debug their models locally with breakpoints, PDB, or whatever they want very easily without them having to worry about what the underlying serving infra will be and how to debug it in that infrastructure. Another issue that it made it hard for developers to make modeling decisions and do several ablation studies was the low correlation of the offline evaluation with the online performance on real traffic, which has been analyzed a lot in recent research as well. One of the core reasons why this happens is because of the inherent selection bias, because we are evaluating a different ranking model, which is the model we are trying to develop, than what was used to log the evaluation data, which is the production model. So, by applying different modern counterfactual evaluation techniques on a small traffic that gets randomized recommendations instead of using a production model, we are able to evaluate a large number of models without the risk and time of having to deploy them to real traffic. The plot shows the correlation between the old evaluation using mean average precision on the left and the new counterfactual evaluation framework on the right. We can clearly see the counterfactual evaluation is quite highly correlated, allowing us to evaluate models and run large hyperparameter tuning easily without waiting for week-long online experiments. Armed with the new tools, we reanalyzed each component of our ranking to gauge the effectiveness of each of them. Based on rigorous ablations and experiments, we found that many of the interaction and the summarization layers that were so helpful for sparse features were actually detrimental for the rich embedding-based signals later introduced in the model. We found that the best choice was to feed these signals directly into wide, fully connected layers and let the model learn how to exploit these signals rather than imposing any bias to the model structure. In this process, we also increased the size of the fully connected layers, in effect increasing the model capacity to better model these relationships. Together, these changes gave to a 4% boost to the engagement metrics in offline evaluation. As expected, this increase in model size led to a corresponding increase in the latency of the model. But as we know, we are in this surface ranking models, we are bound by the allowable latency that we can have to have a good user and pinner experience. So here, having the support of nature PyTorch development helps a lot as we're able to employ some very common industry practices to optimize the model for inference. We used a technique called Int8 Quantization to gain about 4x speed in inference. The Int8 quantization works because inherently Int8 uses 8-bit integer arithmetic instead of floating point numbers and use integer math instead of floating point math, reducing both memory and the computing requirements on CPU. The core idea behind quantization is the resiliency of deep neural networks to noise. This means that these networks can cope with small changes in the weights and the biases of the network resulting from the quantization error and still maintain most of their performance. And there is a growing body of work to reduce this impact on model performance as well. The above diagram on the left shows the flow of how post-training quantization works. It takes a trained model and some calibration dataset to collect activation statistics and use these statistics to bin the weights into int8 space. One of the most important things that we learned here is that the calibration dataset needs to reflect the production traffic for optimal performance, and using the sampled training data leads to very high performance drop in the model when compared to the non-quantized version. This is quite expected, as the bins in the int8 space are decided based on the activity histogram. And if the activities of the calibration dataset is very different from the production traffic, the bins will be miscalibrated. And hence, we need to take care of the calibration dataset we use while performing quantization in a model. One another interesting thing that we do differently in our case is that we only quantize the fully connected hidden layers in a model. We do not quantize the output layer to allow for like a larger range of engagement probability predictions of this model. One thing that happens when you quantize the last layers, because in effect quantization is reducing the space of the output space to 256, is that you reduce the number of unique scores that the model can generate, thereby affecting the quality of the ranking it is generating and causing issues and suboptimality in downstream systems. The table on the left shows the benefits of quantization. The first row shows a model without quantization. Which leads to about 100% increase in latency and 4.4% gain in offline metrics. The quantization model is able to maintain most of this engagement gain with a very small drop in the engagement gain, but not only matches the performance latency of the production model, but leads to a 10% reduction as well. Meaning like you get both engagement gain as well as latency gain, which is not quite ideal always. This totally led to online performance, led to 5% increase in engagement, and also some great savings on infra due to the reduced 10% latency. Excited by this wins, we further invested in exploring different complex and large models, including several state-of-the-art learning to rank models. We found that using a two-layer transformer encoder followed by a fully connected layer worked the best for us, giving us a 4% gain in offline metrics. The self-attention in the transformers allows for rich feature interactions and leads to better utilization of the different spars and the embedding features in the model, leading to a better performance. The table on the slide shows the offline engagement gain of the transformer model when we compare to the other state of the models like DCN and PLE. As we can see, DCN and PLE helps, but the transformer models beats them by about 1.5%. The idea of all these models are similar. Deep and cross networks tries to learn more feature interactions by having a deep layer using fully connected layers and cross layers which are learning different functions of features. PLE follows a mixture of experts approach where they try to learn an expert from the very bottom for each of the different multitasks in the model. Transformer kind of does both of these through the different attention and the multi-heads, and hence performs better in practice. But as you might already be wondering, can these models be actually deployed given the strict low latency requirements we discussed? And you're right. Each of the complex models leads up to 300% increase in latency, which is definitely not getting deployed. Now, since this transformer model was the best performing, we tried to invest in trying to serve this model with little to no increase in latency. The first thing we tried was similar to the wide network, was to quantize this model, but we didn't find any latency improvement, and hence we shifted to our focus to GPU serving, which is the next thing we can try. Since we have seen that the GPUs are very optimum for these self-attention modules, which involve lots of different matrix multiplications and calculations. But contrary to our expectation, we found that the latency on the model on GPU was even worse than on CPU. This observation is non-trivial, but and much different from training, because when we are training these models, we see a huge speed up on GPU when versus training on CPUs. But if you look a little deeper, this makes sense because the training works with larger batch sizes, which is much larger than what we see during inference. During training, we are using batch sizes in thousands, and during inference, we are having batch sizes of hundreds or even less than that. So we decided to look a bit deeper as how we can optimize this model to make it even work for smaller batch sizes on GPU. To get started, we used the NVIDIA's Insight system to profile our model on GPU to understand where the model is spending its time, what is happening, what is taking so much time for the model, and look if we can find some avenue for optimization. The profile above shows the CPU and GPU usage for a single inference run of the model. The profile is quite dense and shows a lot of information, but just let's understand a few key components which will be useful in the talk. The bottom row below the dark black line shows the CUDA API launches, which happens on CPU. The rows above the black line shows the information of the GPU. The first lighter blue line shows the percentage utilization of the GPU by the different running kernels. The next darker blue line shows the exact kernels running on the system. It can be either they can be serial or multiple kernels running at the same time. The green lines in the third row represents the memory operations happening on the GPU, mainly about with different tensors moving to and from GPU. Let's now look at the profile from left to right, which corresponds to the module start of the module execution to the end for the inference. As we can see, there is some data transfer at the start of the model, where the input tensors are being transferred to the GPU. This is followed by many kernel launches and kernel execution on GPU. At the very end, we have some memory transfer again, where the predictions are transferred to CPU. So this gives like an overall picture of how the different operations are happening on GPU for this model. One thing that you can note in this profile is that there are many small kernel launches and execution in the model, and the operations look quite fragmented both on CPU and GPU with very small tiny specks in both the CUDA launches as well as the CUDA kernel executions. Let's zoom into one of these sections. You can see a very interesting pattern. The kernel launch time for many of these operations are more than the actual kernel running time, which means we are wasting time on GPU. It would have been much faster to run this on CPU itself. The source of this inefficient operations are the many feature level operations in the model. We have like different operations like normalization, embedding lookup, projections, and we have lots of small features in the model leading to this fragmented look on GPU that we get. So naturally, to address this, we decided to if we can consolidate the small feature level operations to one big operation that can be run across multiple features instead of running them for each single feature. And we assume this might be more efficient on the GPU. So the first operation that we looked into and optimized was the embedding back lookup. So the left half of the slide shows what was before, like we have multiple features, feature 1 and feature 2 and feature 3, which have different embedding bags of different sizes. Now, to reduce these small operations, which will result from looking up this embeddings back each for each feature, we merge these tables into one large table shown on the right. And now the different regions in this table represents the different feature spaces and different vocabularies corresponding to them. But now having just one embedding bag, we can concatenate all these features and turn them into just one kernel lookup operation, which is one lookup on the GPU, thereby optimizing the fragmented operations. This reduction reduced many small inefficient GPU operations to one bigger and efficient GPU op, as you can see in the profile. Now, the kernel launch time of this large embedding table lookup is negligible when compared to the actual kernel runtime on GPU, which is what we expect when we are trying to use a GPU, that all our operations are on GPU and they consume most time, and the kernel launches are much cheaper when compared to them. This optimization led to about 150% reduction in latency increase as shown in this plot. Motivated by this, we looked at the other feature level operations and see which ones we can optimize. The one that came very evident was the projections. We had a lot of feature projections to project them to a common space that can be fed into the transformer. To now optimize this, we basically constructed a single projection layer, which we're now using batch matrix multiplication kernel, which is just one kernel launch on GPU. Now, hence, this optimization led to a further 100% decrease in latency, as we can see in this figure. So, in total, combining both of these consolidation of the small edge ops helped us decrease the latency increase from 400% to 150%. We are still a long way from the production, but it seems we are going in the correct direction because we are moving where we want to. But now we are at a crossroad. We have optimized all the different feature level operations, but even after this consolidation, we are left with some small feature preprocessing operations, which are per feature like normalization and cannot be merged into together like we merged the projection layer and the embedding layer. So, and this was still the remaining inefficient operations on GPU. But you realize that these ops are faster if you can just run on the CPU and don't use GPU for them. So basically we use this insight and decided to use a mixed model approach. Instead of running the model wholly on CPU or wholly on GPU, we divided the model into components, some of which runs on CPU and some of which runs on GPU. And we made it such that all the CPU layers, which were the feature preprocessing layers, come before all the layers on GPU so that we don't have much memory to and from between GPUs. So now this led to a huge improvement because now you have the small inefficient ops on CPU and all the larger efficient operations on GPU, and we are getting the best of the both worlds. And this led to an improvement in model efficiency, as you can see in the profile. All the kernel launches are small when compared to the actual kernel runtime, with some memory transfer when the model shifts from CPU to GPU. This optimization helped us bring the model latency to within just 10% increase over the current production model, allowing it to be deployed in production. This is a big achievement for us, so like going from a 400% latency increase to just 10% increase and having such high gains and unlocking a new potential to deploy models on GPU. The current model transformer model is currently in A/B experiment and showing similar impressive online results and is expected to be deployed this quarter. Apart from the gains this transformer model, as I was referring to, the GPU serving enabled us to further increase the model capacity and include richer features into the model, which was not possible earlier due to latency considerations. One of the important features is the user activity and the pin engagement sequence data, because it's very informative and it's powerful to drive strong personalization for rich and relevant content. But we used to use like summary statistics for the features in the model due to the latency budgets because we are not able to feed these raw signals directly into the model. But now, with GPU serving available, we experimented with including this raw sequence features into the model and found impressive 8% increase in home feed repin rate in offline metrics. We were able to serve this model on GPU with similar latency to the transformer model and is one of the candidate model in the A/B experiment, showing strong online results and expected to launch this quarter as well. One other interesting thing in the area of learning to rank system that is gaining quite a popularity in the research community is identifying that the implicit feedback data that is used to train these models have a lot of biases, and often addressing these biases leads to better engagement modeling and correspondingly better engagement on the platform. The diagram here shows a typical feedback loop for a recommendation system. Users come to the platform and interact with the content recommended by the current recommendation system. This interaction data is then collected and used to train a new version of the system. This new system then serves recommendation to the users, and this feedback loop and cycle continues. Now, as this data of user interactions are observational rather than being experimental, biases are easily introduced in this data. The recommendation models capture these biases and even scale them, leading to suboptimal decisions. When the user interacts with the system, several biases creep in, like selection bias, like unengaged content is not necessarily non-relevant. Trust bias. Users trust the highly ranked items are more relevant based on how our ability to use the systems. Position bias. Users tend to interact with items in higher position of the recommendation list, regardless of the item's actual preference, because we don't want to scroll a lot, and so on. Since the model Additionally, since the models are trained on a subsample of the data, biases arise due to the sampling strategies and the model structure. And now, since the recommendation systems exhibit uh, the phenomenon of that richer gets richer, we get popularity bias, and some unfairness into the models. So together, there's a lot of scope to address different kinds of biases and improve the engagement prediction performance of our model. So first, to do a risk analysis and to understand what impact we can have by addressing these biases in our system, we started by looking at position bias. The above graph shows the ribbon rate by position. So we try to understand this graph to see what is the impact, how much of these biases exist on our system. And as expected, we see that lower ribbon rate as the position gets lower and lower. The ribbon rate at position 1, 2, 3 are higher, and as we go lower, the ribbon rate reduces. The higher ribbons at these higher positions are a combination of a lot of factors. First, we recommend more relevant items at higher positions because that's the job of a recommendation system. Second is the position bias that we're talking about. And there are multiple other biases as well, the trust bias and so on. So we try to address the position bias. Now, to address this bias, we note that the observed utility or the relevance in the training data can be divided into two components. The actual relevance and utility of the content, which we want to model through our ranking model, and the position model bias in the model. So earlier, when we have nothing and we just train our ranking model on this observed utility, we are fitting the model to predict the observed utility and not the actual utility, which is different due to the bias there. Hence, to address this issue and make the model learn the actual utility, we introduce another small network to learn the position bias as a function of position and other context features. Now, the main ranking model predicts the actual relevance, and we use the learned position bias to fit the data with observed relevance during training. But now during inference, the position bias component is discarded, and we use the main ranking model to obtain the true relevance of the pins, leading to better engagement probability. The figure on the bottom right shows the learned position bias for each position for a particular context, which in this case is iPhone. From the figure, we see that the learned bias is smaller for a lower position up to position 3 and then again increases following a similar trend as ribbon rate. If we think about it, this quite corresponds to the behavior that we can see on iPhone. The iPhone screens are smaller, and on Pinterest, you typically see 3 to 4 pins on your first screen, and as you scroll, you go to other pins. Hence, we see the graphs kind of capture what is generally expected, and hence we are confident the model is learning something important, which can help the model be better at prediction. So this simple bias correction during training led us to 1% increase in offline and online experiments, showing the potential for investing in this area more. And this is one of the focus areas this year. In summary, today we went over the history of our ranking model and our most recent works in pushing the limits for this model. We learned that the representations are critical to recommendation systems as they disentangle the complex representation models from the latency sensitive ranking models. One of our great learnings have been that offline model iteration speed is critical to unlock huge performance improvements, as this enables the developer, the ML engineer, or the ML modeler working on these models to make quick decisions, quick ablation studies offline without waiting on complicated serving infrastructures, then online experiment, and so on. And this ability can help discover many new architectures as well as many new advancements in the modeling. The exceptional gains for both the large linear model as well as the transformer model shows that large capacity models are extremely useful, and if we can serve these models with low latency, we can unlock huge engagement benefits. One thing to keep in mind when working on these web-scale ranking models is that many commonplace techniques which are generally applicable might not directly apply to the use case and might need some experimentation and understanding to make it work, as we discussed how we made quantization work for our model. The GPU serving effort shows that how critical the GPU usage pattern and how the kernel launches and the kernel execution which depends on the model architecture, is to effectively serve these complex models on GPU. And we are beginning to scratch the surface, and we plan to deep dive more into this area because it's quite interesting for us. One common underlying theme all throughout this evolution of the model that we have observed is that investment in core capabilities like the AutoML model, the representation learning features, counterfactual evaluation, or GPU serving not only gives immediate returns, but also opens up the avenue for much bigger gains in the future. So that's all from me, and thanks for joining us today for the talk, and I hope you really enjoyed it. Now we move to the question answering session, and we'll continue answering any questions that you might have. Thank you, and have a good day.